the metal that powers the planet. Every second, 3 electric cars are sold worldwide. Every hour, 50,000 smartphones roll off production lines, and all of them depend on one element: lithium, the white gold of the 21st century. The lightest metal on Earth, which you'll never see in its pure form because it instantly explodes on contact with water. But it's what fires up your phone, drives electric vehicles, and will power humanity's future. How do salt lakes high in the Andes transform into an energy source for billions of devices? You'll discover why lithium is called white gold, how giant evaporation pools the size of a city work, and why a real geopolitical war has erupted over this metal. Watch until the end. The finale will reveal what's behind every percentage point of your smartphone's battery. This is the story of a metal that changed the world in just 20 years.
Lithium's story began in 1817 on a tiny Swedish island called Uto. A young chemist, Johan August Arfwedson, was analyzing a rare mineral called petalite when he discovered something strange. This was a metal, but incredibly light, lighter than water. Arfwedson named it lithium from the Greek word lithos, stone. Ironic, right? A stone that floats. In 1821, British chemist William Brine first isolated pure metallic lithium through electrolysis of molten salt. What he saw blew his mind. A silvery white metal so soft you could slice it with a knife like butter, and so light that a chunk of lithium actually floats on water. But that contact with water, it lasts maybe a second. Lithium instantly explodes into a violent reaction, hissing, smoking, and it can catch fire. For 150 years, lithium was just a lab curiosity. They used it in medicine to treat mental disorders, in glass and ceramic production. But everything changed in the 90s. In 1991, Sony released the first commercial lithium-ion battery. It was a breakthrough. Before that, batteries were heavy, short-lived, drained fast. Lithium-ion batteries turned out to be 3 times lighter and held their charge way longer. The portable electronics revolution began. Cell phones became compact, laptops became light, cameras became long-lasting. But the real explosion in demand happened in the 2010s when electric vehicles hit the market. Tesla, Nissan, BMW all built their cars on lithium-ion batteries. One electric vehicle requires 130 to 175 pounds of lithium. For comparison, a smartphone contains just 1/10 of an ounce. Demand for lithium jumped from 30,000 tons in 2010 to 550,000 tons in 2023, and that's just the beginning. Forecasts predict 3 million tons by 2030. Lithium transformed from a rare lab element into a strategic resource more important than oil. But where do you get that much lithium? On Earth, lithium isn't rare. It's the 33rd most abundant element. But here's the thing. Concentrated deposits, not so common. There are 2 main sources, hard rock and salt brines. Hard rock means spodumene, a rare mineral mined in Australia, Canada, Zimbabwe. But the future? It's in the brines. High up in the salt lakes of South America, at 10 to 13,000 feet above sea level, lie the planet's largest lithium reserves. It's called the Lithium Triangle: Bolivia, Chile, and Argentina. Bolivia's Salar de Uyuni is the biggest salt flat on Earth. 4,000 square miles of blinding white salt under an endless sky. Looks like a massive frozen lake. Beneath that salt crust, brine, containing about 9 million tons of lithium. That's half the world's reserves. Chile's Atacama, the driest desert on the planet. Here too, massive lithium deposits hide in underground brines.
Now, let's break down how lithium is actually extracted from these salt lakes. The process looks almost magical.
First, they drill wells anywhere from 65 to 330 feet deep. Powerful pumps suck up brine from these wells, a salty liquid similar to seawater, but way more concentrated. A single liter of this brine contains anywhere from 300 to 1,500 milligrams of lithium. For comparison, seawater has just 0.17 milligrams per liter. The pumped brine gets channeled into massive evaporation ponds. Picture this, artificial lakes covering dozens of hectares. From above, they look like giant colored squares, blue, turquoise, green, yellow. The color depends on mineral concentration and microorganisms. These ponds are arranged in a cascade, like giant steps. The brine flows from one pond to the next, and at each step, the magic of evaporation happens.
Under the scorching sun of the high-altitude desert and relentless winds, the water evaporates, slowly, month after month. The Atacama receives less than a millimeter of rainfall per year, but the sun shines 300 days a year, perfect conditions for evaporation. The lithium concentration in the brine gradually increases. First, unwanted salts precipitate out of the solution, sodium chloride, sulfates. They're collected and removed. The process takes 12 to 18 months. Yeah, you heard that right. Over a year just waiting for the sun to do its work. During this time, the lithium concentration grows by roughly 20 times. What started as a weak brine transforms into a thick, oily solution containing about 6% lithium. The brine turns amber yellow, almost like honey. It's pumped into specialized tanks and shipped to a chemical plant. Here begins the final stage of transforming salt water into white gold.
At the plant, concentrated brine is treated with sodium carbonate, basically baking soda. A chemical reaction happens and a white precipitate crashes out of solution, lithium carbonate. It's not the metal yet, but it's a crucial compound. The precipitate gets filtered, washed, dried. What you end up with are fine white crystals, like powdered sugar. That's why lithium's called white gold. It actually is white. Lithium carbonate gets bagged up and shipped all over the world. Most of it goes to China, Japan, South Korea, wherever batteries are made. But that's not the end of the road. To make batteries, you need lithium hydroxide. Lithium carbonate gets dissolved in water, treated with calcium hydroxide. You get a solution of lithium hydroxide, which then gets evaporated. What remains are white crystals of lithium hydroxide, the final product, ready for manufacturing battery cathodes. The whole cycle, from pumping brine to getting the finished product, takes about 2 years.
There's another method for extracting lithium, from hard rock deposits. In Australia and China, they mine spodumene, a mineral that contains lithium. They blast the rock, crush it, grind it into dust. Then they heat it to 1900 degrees Fahrenheit in massive rotating kilns. At that temperature, the spodumene changes its structure, becomes more reactive. The roasted rock gets mixed with sulfuric acid. A violent reaction kicks off, releasing heat and toxic gases. The lithium moves into a lithium sulfate solution. This solution gets purified of impurities, treated with sodium carbonate. Lithium carbonate precipitates out, the same product as from the brines. But this method is way more energy intensive and expensive. You need high temperatures, massive volumes of chemicals, tons of waste gets generated. That's why the future belongs to brines. Even though right now about 60% of the world's lithium comes from hard rock, the balance is gradually shifting towards salt lakes.
Now let's look at where all this extracted lithium goes. 75% of global production goes into batteries. A lithium-ion battery is a complex device. Inside are 2 electrodes, a cathode made of lithium oxide with cobalt or manganese, and an anode made of graphite. Between them is an electrolyte containing lithium salts. During charging, lithium ions move from the cathode to the anode and slide between the graphite layers. During discharge, they move back, and this flow creates an electrical current. Brilliant simplicity. Lithium is ideal for this because it's the lightest metal capable of giving up electrons. A single lithium atom weighs just 7 atomic units. For comparison, lead weighs 207. That's why lithium batteries are so light and energy dense. A modern Tesla Model 3 electric vehicle contains about 24 pounds of pure lithium in its 1,060-pound battery. This battery can travel over 300 miles on a single charge. Beyond batteries, lithium is used in ceramics and glass production. It lowers melting temperatures and makes materials stronger. In metallurgy, lithium gets added to aluminum alloys, makes them lighter and tougher. In nuclear power, lithium produces tritium. In medicine, lithium carbonate is still used to treat bipolar disorder, stabilizes mood. Global lithium production in 2023 hit around 130,000 tons of pure metal equivalent. The major producers, Australia, 40%, Chile, 25%, China, 14%. Lithium prices rocketed from $5,000 per ton in 2020 to $80,000 in 2022, then crashed to $30,000. The market's volatile because demand is growing faster than supply. A real geopolitical battle has erupted over lithium. China's buying up deposits worldwide. The US is trying to build its own supply chain. Europe's hunting for alternative sources. And just like that, having journeyed from salt lakes high in the Andes through 18 months of evaporation under the merciless desert sun, through chemical plants and the most complex purification processes, lithium emerges into the world, the white gold of the 21st century, the lightest metal that powers modern civilization. This is the story of how humanity learned to turn salt water from ancient lakes into energy for billions of devices. Every time you charge your smartphone, get into an electric vehicle, or fire up your laptop, remember, inside beats a heart made of lithium, the metal for which we mine deserts and drain salt flats. The metal behind the energy revolution and the move away from oil. The metal without which the future of humanity is unimaginable. White gold extracted from snow-white salt lakes to power the planet with the energy of tomorrow. Lithium isn't just an element on the periodic table. It's the key to a future that's already here.
And now imagine what holds enormous suspension bridges in the air, which daily withstand the weight of thousands of cars and hurricane-force wind gusts. Not concrete and not steel in the columns, but an invisible hero, steel cable. From thin, almost fragile wires, they create structures capable of bearing hundreds of tons. The secret lies in technology that transforms a simple metal rod into a sinew that never gives in. American factories have already woven over 800,000 kilometers of cables, and each meter is like a separate artery of civilization. But there's a detail that's not written about in textbooks, and you'll discover it only at the end of this video. Everything begins with selecting raw materials, high-quality steel wire that must possess exceptional strength and flexibility. These wires pass through a cold drawing process, where thick steel rods are pulled through special holes, gradually reducing their diameter to thin but extraordinarily strong threads. This process doesn't simply make the wire thinner, it enhances its mechanical properties, making it resistant to breaking. Imagine that each meter of this wire can withstand enormous loads whilst remaining flexible and elastic. After the wire is ready, the most interesting part begins, forming the steel cable. Dozens and sometimes hundreds of such threads are twisted into strands, then woven into complex structures. Each wire layer has its purpose. Internal threads bear the main load, whilst external ones protect against wear and corrosion. The entire process resembles creating living tissue, where each thread is a separate vein that together forms a strong and reliable whole. Particularly impressive is the precision and control with which these cables are manufactured. Each stage is accompanied by strict testing. They check tensile strength, resistance to bending, and impact of weather conditions. Testing is conducted using special equipment that simulates the loads the cable will experience during bridge operation. This is extremely important, as bridges often stand in humid environments or in locations with aggressive climates. Thanks to these coatings, cables not only maintain their strength, but also extend the bridge's service life, ensuring safety and reliability. Imagine the production scale. Factories that can manufacture thousands of tons of steel cables annually, unwinding and weaving hundreds of kilometers of wire. American manufacturers, for example, have many years' experience and employ the most modern technologies, allowing them to create cables for the world's most famous bridges. It's known that American Bridge Company has laid over 800,000 kilometers of steel cables for suspension bridges. Another aspect that impressed me is the role of engineers and technologists who constantly improve production processes. They work to make cables even stronger, lighter, and more resistant to extreme loads. Using new alloys, improving twisting and coating methods, all this makes modern steel cables genuine masterpieces of engineering thought. During the tour, I saw how enormous spools of steel wire move smoothly along conveyors, how wire passes through cold drawing, and how craftsmen control every centimeter of this process. American manufacturers, such as American Bridge Company, have enormous experience in manufacturing steel cables for the country's largest and most famous bridges. They produce thousands of tons of cables annually using modern technologies and strict quality control. It's known that for suspension bridges, they use cables with multi-layered structure that can withstand loads of hundreds of tons per square centimeter. During Brooklyn Bridge construction, for example, each of the main cables consisted of 19 separate strands, and each strand of 278 wires. This provided an enormous strength reserve. Steel cable production in the U.S. is a combination of tradition and innovation, where the craftsmanship of engineers and technologists is complemented by automated lines and modern equipment. Each stage, from raw material selection to protective coating application, is controlled with maximum attention, as thousands of people's safety who daily use bridges depends on this. European enterprises, particularly in countries like Germany, France, Italy, as well as Ukraine, Romania, and Poland, play an important role in supplying steel cables for bridge construction of various scales. Modern bridges are the result of millennia of engineering thought development, where traditions, innovations, and the most modern materials combine. They not only perform the function of connecting shores, but also become city symbols, cultural monuments, and technical masterpieces. Modern engineering marvels include the Falkirk Wheel in Scotland, a unique rotating boat lift that connects two canals and allows lifting boats through 180 degrees. This structure is not only functional, but also impresses with its futuristic design. Cable-stayed bridges, such as the Golden Gate in San Francisco, demonstrate the application of steel cables that withstand enormous loads and ensure structure longevity. Somewhere in the world right now, a concrete giant is being born, capable of spanning a space as wide as an entire basketball court, and all of this without a single support. How can a lightweight hollow slab withstand the weight of hundreds of tons? Why do builders say that within these slabs lies the power of steel muscles? And most importantly, what secret makes them so unique that annually in North America, over 17.5 million square meters of these structures are produced, the area of 30 pentagons? Stay until the end, and you'll discover the secret that will forever change your understanding of concrete. The slip former machine crawls along a 590-foot forming bed at approximately 4 feet per minute. Doesn't sound terribly fast? Now let's do the maths. That's 200 feet per hour. That's nearly the length of an Olympic swimming pool, born from concrete in less than an hour. During a single 10-hour shift, one such bed can churn out almost half a mile of perfectly formed concrete slab. Now for the main feature, the voids. These holes inside aren't simply for aesthetics. They reduce the slab's weight by nearly 50% compared to a solid slab of the same thickness. Imagine constructing an office center with a floor area of 100,000 square feet. If the floors were made from ordinary solid concrete, their weight would be approximately 5,000 tons. But with hollow core slabs, just 3,000 tons. We've just removed 2,000 tons of excess weight from the building. That's the weight of roughly 500 adult elephants, which foundations and columns no longer need to support. This allows the entire building structure to be made lighter, more elegant, and most importantly, considerably cheaper. But how can such a lightweight slab be strong? The secret lies in those tension steel muscles. The concrete used in these slabs isn't what you have on your pavement. This is high-strength concrete, withstanding pressure exceeding 8,000 pounds per square inch, whilst ordinary concrete manages only 3,000 or 4,000. And the steel cables inside are tensioned with such force that they create constant compression within the slab. That's precisely why these slabs are adored for constructing car parks, supermarkets, and open-plan offices. Annually in North America, over 17.5 million square meters of hollow core floor slabs are produced. This figure simply doesn't fit in one's head. It's an area sufficient to construct 30 buildings as gigantic as the Pentagon. Every year. This isn't merely a building material, it's an entire industry built on speed, efficiency, and intelligent use of resources. Everything begins not in a concrete mixer, but on a gigantic, perfectly flat aerodrome inside the workshop. This is the forming bed. Imagine a perfectly level, polished steel runway several feet wide, but in length 400, 500, and sometimes 600 feet. Beneath this runway lie pipes through which hot water or steam circulates to keep it warm. At both ends of this runway stand massive steel anchors embedded in thick concrete foundations. Between these two anchors, high-strength steel cables or strands are tensioned. This isn't ordinary wire. It's several steel threads woven together, each capable of supporting the weight of a motor car. They're laid along the entire length of the 590-foot bed, forming the future skeleton of the slab. One end of each cable is securely fixed in the anchor. To the other end is connected a gigantic hydraulic jack, and this jack begins to pull. It tensions each of these steel cables with a force of 30 or 40,000 pounds. The steel muscles tense up, becoming as hard as the strings of a gigantic guitar and store colossal energy within themselves. This is secret number 1, pre-stressing. When the steel skeleton is tensioned, the main character enters the stage, the forming machine or slip former. This is one of the most astonishing machines in the construction world. Imagine a strange, squat, self-propelled creature that slowly crawls along rails beside our long bed. At the top, it has a large hopper into which concrete is poured. But this isn't ordinary liquid concrete. This is so-called zero-slump concrete. It's so dry that it resembles damp earth. And so this machine begins its slow journey. Secondly, special vibrators and compactors with incredible force tamp this dry mixture, making it extraordinarily dense. And thirdly, most importantly, inside the machine are special forming tubes that, whilst vibrating, pass through the thickness of the concrete, leaving behind perfectly round, smooth voids. The machine, like a gigantic concrete snail, slowly crawls forward, and behind it, like a trail, remains a perfectly formed, endless concrete slab. Because the concrete is so dry, it instantly holds its shape and doesn't spread. This is secret number 2, voids that make the slab 50% lighter than a solid one. When the machine reaches the end of the 590-foot bed, its work is complete. But our slab is still green and weak. The time arrives for a spa treatment. Workers cover the entire length of this concrete ribbon with enormous insulating tarpaulins. Hot steam is fed beneath these tarpaulins. This creates a sauna effect that dramatically accelerates the chemical reaction of concrete hardening. Under normal conditions, concrete needs weeks to gain full strength. But in this hot, humid atmosphere, it reaches the required strength, over 5,000 pounds per square inch, in just 12 or 24 hours. When the concrete has hardened, the moment of release arrives. Workers slowly release the tension on the hydraulic jacks. Now it's not simply concrete, it's pre-stressed or compressed. This means that when a load acts upon it from above, attempting to bend it, it must first overcome this built-in compression force. This is precisely what allows it to span enormous distances without additional supports. And the final act of this performance? Cutting. Along rails beside our long concrete ribbon travels a gigantic saw. This is a monster with an enormous disc covered in industrial diamonds. With a deafening roar and fountain of sparks and water, this saw cuts the slab with incredible precision into pieces of the required length. Ready, perfectly level, lightweight, and incredibly strong slabs are lifted by gigantic cranes and loaded onto lorries.